Wow. That breathtaking visualization animation really just gets my heart pounding every time I see it. Um, I want to, first of all, welcome everyone here joining us for this webinar. I want to welcome everybody to the School of Earth and Space Exploration's Mission Operations Center. And especially want to thank NASA's Mars Exploration Program and the mission team who are making this exciting landing event possible. And certainly want to also thank our School of Earth and Space Exploration Community Outreach Group team for making this webinar possible. My name is Minnie Wadwa, and I'm a planetary scientist and an educator interested in understanding the formation and evolution of the solar system and planets, especially Mars. I'm director of the School of Earth and Space Exploration and professor here, and I'll be your moderator for this afternoon. Just a couple of reminders for our audience who are joining us right now. You're muted by default. The chat feature is not available. Please submit your questions using the Q&A button, and we will definitely try to get to as many questions as possible here. For best viewing, I also recommend that you select the Fit to Window feature in the upper right-hand corner of your video screen. And also just request that you please be respectful and mindful of our panelists and fellow attendees. And as I said, we will try to answer as many of the questions as time allows. Today, we have a really exciting panel of experts from ASU, including the Mastcam-Z instrument that's on the Perseverance rover. The PI for that particular instrument, Jim Bell, is here. And also a team member from Mastcam-Z, Ernest Cisneros, is joining us on camera right now, but we will also be talking to a few of the other Mastcam-Z team members, including Mohini Jodhpurkar, and Sammy Jacob, who will offer us some updates on high priority science goals for Mars exploration and search for life on Mars. So we'll keep an eye also on the NASA live feed. So hopefully everybody will keep on top of that. And so, yeah, let's get started here. First of all, hey, Jim, how are you feeling, first of all?
Minnie, It's so great to be here. It's so great to share this experience with our CC family, with our friends and family around the country, around the world, I suspect. Last count, there was something like 1,300, 1,400, 1,500 people that are going to join us today, which is spectacular. See, now you have the luxury of being the moderator, which means you can be moderate. I'm going to be freaking out. I'm going crazy. This is really, really awesome. We're super excited. We're here in the ground floor of ISTB4 building on the Tempe campus, where our Mission Operations Center is, right behind me. We're all wearing masks. There's a camera crew here, and we're all going to stay safe, so we're going to keep our masks on. And we'll get some shots inside Mission Operations here in a bit. Our professional operations staff for MASCAMZ is working. They're actually on shift. We're expecting some telemetry from the spacecraft a little later after the landing. So they're doing some coding and prepping and all that kind of stuff. So they're hard at work. And we're just obviously, I mean, look, 7.5 years ago, NASA sent out to the entire world this announcement of opportunity. It said, hey, we're going to be sending a rover to Mars. We're going to launch it in 2020. We want great science instruments on this rover. Here's the goals of the rover. What instrument are you going to provide? What can your institution do to contribute to this mission? And they got something like 50 proposals from all around the world. And we proposed a camera system. This was in 2013, early 2014. And wrote the proposal. A lot of folks here at ASU, faculty, staff, students chipping in, colleagues around the country, around the world. You know what it's like. You've written these big proposals yourself. It takes a lot of work. You end up with this giant stack of papers with all kinds of details and information. And then you just send it off, and you never know what's going to happen. And then something like 6 months later, I got just a wonderful phone call from Jim Green, who was running the Planetary Science Division at the time, and said, hey, guess what? And I said, what, Jim? And he said, you're going to Mars. I said, all right, that's great. We're super excited. And so that was 7 years ago. And so, you know, we've been marching down this trail since then.
Long time making, right?
Yeah.
So hey, I want to ask Ernest as well. How are you doing, Ernest? Are you sitting up straight?
I'm sitting up straight. Yeah, a little bit tired. We've been putting in a lot of long hours leading up to this landing event, but yeah, we're doing good. Getting ready. Excited. Right. Earlier, I feel like I want to break out in song and dance. I'm so excited.
No, I'm trying to hold it in. I'm kind of freaking out too, actually. Moderators. No, it's super exciting for the whole, you know, the school, of course, for ASU. I mean, it's a big deal, and big deal for the world, really. I mean, what an exciting thing to be actually landing this rover on Mars today. So. They want to know, actually, there's a question from Sadie Babbitts. I want to ask that first. I mean, what is the atmosphere like in the room, in the mission operations room behind you? Can you tell? Are you able to sort of infer anything from what's going on back there?
Yeah, I mean, you know, we've been going in and out, and of course, you know, the staff has been preparing for this for years. We've done a whole bunch of practices, simulations. Trying to testing with the analog rover out in the Mars yard in Pasadena with some copies of our cameras on that. And so, you know, I think there's a mood of anticipation, excitement, nervousness. This is a risky business. And I think, you know, kind of like what Ernest was saying, at least myself, I feel like singing and dancing and throwing up at the same time. So it's kind of one of those, you know, feel it in your stomach kind of things when these missions, they come to a focal point. You know, launch was our last focal point last July 30th. That was, you know, we did a webinar then, and there was a lot of stress and, you know, and of course this is completely out of our control. It's out of the engineers' control who built the system now. It's all happening automatically. And the big events for this landing will start in approximately 1 hour.
Wow, no, that's super, super, super exciting. So actually, here's a sort of general question to start out with. This is from Linda Ginsburg, who asks, how did Perseverance get its name?
That's a great question. Do you want to do that? Do you know that one? Remember
The basic background, I
Go
don't
for it.
remember. So in the past, with these Mars rovers, NASA holds a competition for school kids, and you write an exposition. I think the rover should be named this name, and here's why. And these all go into NASA, and then there's a panel of people that make a selection. And so with Mars 2020, probably about a year ago, they started the submission process for those expositions from the kids, and then they went through a review process, and then there was a big unveiling of the name. And unfortunately, I can't remember the young gentleman's name who was selected, their name, but they get the honor of naming the rover Perseverance, and that's how it got its name. So some lucky kids out there going on the, I named the rover, I named the rover.
Exactly.
Great bragging rights.
Yeah, so somewhat, I guess, people are going to be asking about this. When's the earliest signal from Perseverance expected after landing?
So if everything goes as planned, we'll be getting a constant stream of radio signals starting before landing, before the spacecraft hits the top of the atmosphere. At around 12:38 Pacific, 1:38 Arizona time, the cruise stage solar panel will separate, and the rest of the spacecraft will keep going towards Mars. And it's transmitting a signal through the protective cover of the spacecraft. A very simple signal, almost like a semaphore, like somebody holding up flags. You know, okay, hitting the atmosphere now. All right, now deploying the parachute. You know, just simple changes in radio frequency that alert the folks back here 11 and a half minutes later that those events are happening. So we'll be monitoring that all the way down to the surface, watching for the different events to unfold. And then typically, if this unfolds like it has in the past, there's a little bit of a few tens of seconds to a minute when the dust is settling, literally, after the retro rockets and all that, where we probably won't hear anything, and then it has to relock its signal on the orbiter, the Mars Reconnaissance Orbiter, which is in orbit. It's this beautiful dance, Minnie, that's being choreographed with the rover going down and the orbiters up above, you know, passing over at exactly the right place at the right time, and the radio signal going up to the orbiter and being relayed to the Earth. And that orbiter will keep track of the rover after landing for a few minutes. And the plan is to just burst a whole bunch of telemetry on the health of the systems, the status of the rover, the pixel that we landed in. We should know our landing site very quickly in that initial telemetry, as well as within a few minutes of landing, some pictures from the wide-angle hazard cameras down low that can look forward, one back. They have their dust covers on, so they could be really dirty, gritty looking pictures because there's expected to be rocks and dust and spray all over the place. So that the covers are staying on to protect the cameras, and we'll take pictures through them just to prove the cameras are working, to prove that we're safe on the ground. Those could be the first things that we see right around, that'd be right around 1 o'clock, 12:55, 1 o'clock Pacific or 2 o'clock Arizona time, if everything goes well.
Oh yeah, fingers crossed here.
Yeah.
That's great. Yeah. So Kelly Reading asks, how many miles has the rover, actually the vehicle, traveled, and at what speed?
That's a great question, and I have a cheat sheet here. With the rover has traveled 292.4 million miles out of its 292.5 million mile journey to Mars. It's 127 million miles from Earth. It's traveling 65,000 miles an hour relative to the Earth, and 6,700 miles an hour relative to Mars. and the one-way light time is 11 minutes and 21 seconds. So that's important because, you know, we're going to get that signal back from this 7 minutes of terror, it's called. But by the time when we get that first part of that signal, it's actually all over. It's all happened. Spacecraft is on Mars already.
Yeah.
And it's just that, you know, it's so far away. That's how long it takes at the speed of light for the signal to get to us.
Yeah. Wow. So in total, how long has a flight to Mars been for the vehicle?
Let's see, we launched on July 30th.
Yep.
Mm-hmm.
So that's 7 months-ish, right?
Yeah.
Yep. Yep. And that's a pretty quick trip.
Yeah.
It can be as up to a year if the planets are aligned slightly differently. So that's a pretty quick trip, just about as fast as we can go.
Yeah.
You know, I was wondering, I thought maybe it'd be good if Ernest could tell us a little bit more about this facility. He's actually the director of this operations facility. And I
Yeah.
know a lot of people, when they come to IST-B4, they walk past this big fishbowl on the ground floor here, and maybe tell us more about what's going on there.
Sure. Yeah, so the mission operations area, as Jim behind us here, is this sort of patterned over the center of the universe at JPL, where when you see those pictures of all those consoles lined up for missions. So we have a series of computer systems where right now the Mastcam Z team, operations team is back on there sitting. They've got windows pulled up. They're looking at information that's being, as Jim said, coming back from the spacecraft right now, the telemetry. And so this is where all of the work that's going to get done during the lifetime of the mission of Perseverance, where we'll look at the image. We have computer systems situated throughout the building and on campus that do processing of that imagery, and then we'll serve it up on websites to our science team and on our public website as well. And so in addition to the Mars 2020 mission, we'll be doing Psyche imager operations out of there. We have a CubeSat called Luna HMAP that will be getting launched on the SLS. It's a small CubeSat that has a neutron spectrometer. They'll be looking at the poles of the moon. And so they'll actually be flying the spacecraft and doing all the instrument operations also out of that, of the facility behind us. So it is really a multi-mission, multi-instrument operation center that's, I think, one of the crowning jewels along with all of the other facilities that we have here at CC.
Yeah. That's great. Well, thanks so much, Ernest, for giving us that virtual tour. So here's a question about, I think we indirectly kind of answered this, but just explicitly, you know, how long does it take basically to send commands to the rover? And how long does it take for images to transfer from Mars to ASU?
Yeah, those are great questions. And the answer is probably not obvious, but the answer is it depends. So first of all, we don't actually send commands to the spacecraft from here. They don't, you know, NASA doesn't trust us that much to do that. So we and other instrument teams around the country, around the world, are actually sending our commands into JPL, Jet Propulsion Lab in Pasadena. Our commanding is actually done by our colleagues at a company called Malin Space Science Systems in San Diego. We do the downlink side here at ASU, the bits coming down from the spacecraft. They are responsible for the uplink side, sending the commands up to the spacecraft, or in this case, to JPL, where they're merged with all the other commands and requests from all the instruments. And there's kind of a little bit of a collegial fight that goes on. Oh, we only have so much power. We only have so much data volume. We only have so much time. You know, and so there's an adjudication process that the team does to decide what to fit into the plan. It's kind of like a Tetris game. You got to fit the pieces in and fill up every single bit of time and power, data volume. And so we've got our sequences then become part of that planning process. And then JPL uses NASA's giant telescopes in the Deep Space Network in California, Spain, and Australia. One of them will be lined up right. And once all those commands are assembled and tested, verified, They get radioed up to the rover just in time for the rover to have woken up in the morning. The rover wakes up in the morning as the temperature gets warm enough that it doesn't have to hunker down and use its heaters, wakes up, starts listening for that set of instructions, that to-do list from the Earth, and the Earth radios that to the rover, and it's like a bunch of time-tagged thing. Okay, at this time, take this little panorama. At this time, drive 10 meters forward. At this time, put the arm out. This time, make a weather measurement. And some of it's done in parallel, and it's all very carefully choreographed. And then the rover gets those commands and just goes and does it. There's no joysticking it. You know, we're not monitoring it in real time, watching what it does. It takes pictures, takes other measurements, stores them in its computer memory. And then every data product, every picture has a priority associated with it. And near the end of the rover day, as the temperatures are starting to drop again, it's getting too cold to operate, we get ready to relay all that information to one of the NASA orbiters or one of the European orbiters that are orbiting around Mars that act as our relay satellite. So every one of those opportunities is different. Sometimes we can send a lot of data, sometimes we can send a little data. Just depends on where they are in the sky and all that kind of stuff. But we relay as much as we can, take that priority list, get through as much as we can, and there's a lot more below the list that then gets moved up in priority for the next day. And there's a whole bunch that stays in low priority that's not going to come down for weeks. Maybe it's not going to affect driving tomorrow. Maybe it's not going to affect the arm drilling tomorrow. That stuff has the highest priority, and that comes down immediately. So some of our pictures will be in that priority level. We want to help the rover drivers drive, and so we take beautiful stereo images at high resolution, and they need them immediately to figure out how best to drive tomorrow. Or the arm placement for drilling onto a rock. They need that information for the planning tomorrow, so that'll be high priority. So those images we would get down pretty quickly, the same Mars day. So maybe within 4 or 5 hours or less of taking them. Conversely, there might be some images of some distant target that I'm interested in, or one of my students is interested in scientifically, and we're going to study that in the images in detail, but it's not going to affect tactical operations. It can wait days, maybe weeks to come down in that big queue, that big bucket of data that's waiting to come down to Mars. And so that could take weeks to come down. But typically, we're sending commands up once a day, and we're getting 1 or maybe 2 bursts of data back to the Earth in the afternoon on Mars. Or in the middle of the night, those orbiters will come back around and make another pass. So that's why it's a complicated answer. That depends.
Yeah, got it. So you mentioned that the rover drivers at JPL, they're going to be driving the rover, but this rover's got some autonomous terrain navigation capability. And can you say anything about that? Is there anything new here that's being utilized for this particular rover as opposed to the previous ones?
Yeah, this is the terrain relative navigation is the new and, to me, scary part about this landing. You know, previous Mars landers, the scientists and engineers have done a really good job of making sure that we picked a relatively flat place free of hazards. Not completely free of hazards. At tiny, tiny scale, we might not be able to tell. But at macroscopic scale, we knew pretty flat. But this landing site, Jezero, there are cliffs and mesas and fractures in the ground. I mean, there's a lot of hazards, and we know that in advance, and we're intentionally still going there. And so the active terrain navigation system has a map on board the rover, has a map in its computer of those hazards. And as it's coming down, it's taking pictures, comparing the pictures to the map automatically in its computer, lining it up, figure out, oh, that's where we are. Oh, you know what? I'm heading too close to that mesa. I'm going to fire the jet. Shh, go a little bit to the right. Avoid that. Oh, I'm getting a little too close to that cliff. Let's go back a little bit. Okay. And that system is going to guide us to a safe spot. in that map.
Mm.
What could possibly go wrong?
I know. Wow. Yeah. No, that's incredible. So here's a question from Martin Crawford, who asks, how powerful is a computer that manages the landing?
There's actually two computers. I don't know if you know the details.
I don't.
Oh, you're the computer guy.
I know. Too many computers.
Yeah.
There's a lot of-
There's two computers. I know the one that's doing the terrain checking that I just talked about is more modern and faster and working very quickly, but I don't know its clock speed in megahertz or anything like that. The one that's doing the regular driving of the rover is a little bit faster than Curiosity's, but still nothing like your laptop or a supercomputer or something like that. You know, one of the challenges that NASA has is that we can't always fly the most cutting edge technology because it hasn't yet been demonstrated to work in space. And so these slower, older computers, we know they'll work in that environment. We know they can handle the shocks and the vibration and the vacuum of space and all that kind of stuff. So we trade that reliability for the speed. And it turns out the speed is good enough. We don't need, you know, whatever gigahertz speed that you can get off the shelf nowadays. Although over time, the computers will catch up to commercial technology.
Yeah, right. So actually, here's a question from Stephen Haran, who asks, what's the expected duration of the mission once Perseverance lands? So maybe you want to just talk a little bit about the timeline for the expected lifetime of the mission and what the timeline is expected to be.
Yeah, so you know, every one of these landers and rovers has what's called a prime mission. That's from the beginning to some point that's determined to be okay. Let's see if we can succeed with the mission by that point. You know, you might remember that Spirit and Opportunity back in the early 2000s were prime missions of 90 days on Mars, and then they did extended missions after that. Curiosity rover prime mission of about a year, a Mars year. It's doing extended operations beyond that. Our prime mission for Perseverance is also a Mars year, which is a little more than 2 Earth years. And so we're going to work hard to collect samples and get them ready for caching on the surface in that prime mission time. But the expectation is if we land successfully, if we're operating successfully for a Mars year, we'll probably keep going and last longer than that. We have to write a proposal to NASA and justify continuing to run the mission if everything is healthy and we're still making great progress. And if so, we would continue on with an extended mission. So the systems have been qualified by the engineers for I believe 3 Mars years. That's what sort of the manufacturer's warranty is. But I would love to get the extended warranty on this vehicle, absolutely.
Yeah, no, we would totally love to have extended warranty, especially because what that means is that, you know, when we actually go to pick up the samples, there's a possibility that maybe if Perseverance is still operating, it can actually bring another stash of materials to the landing, you know, the landing site for that sample return mission, because that'll really kind of help to maybe bring back as many samples as we can possibly get. So I'm
hey, Minnie, I was wondering, maybe we can swap in a couple of the students.
Yeah,
please do. We can have Sammy and Mohini come in and you can chat with them for a bit and learn about what they're working on.
Absolutely.
If they're available. Are they here? You guys ready? All right, let's do a little swapper. I don't know if Kim wants to show a video or something while we're doing that, but we can.
Oh, maybe while they get set up, Jim, you could answer a question or so.
Sure.
Well, so actually, one thing that Christina Mold asks is, you know, in what way is this landing different than previous ones? And in that case, I mean, I want you to maybe say a little bit of something about the pinpoint capability of this particular.
Right. So we are heading for a tiny little place on a planet, you know, 150 million miles away, a very small crater that's only about 50 kilometers across, and we're trying to hit a target on the west side of that crater that itself is only 5 to 10 kilometers across. So we have this 10-kilometer what is that, 6 mile or so wide circle that the engineers are aiming us for. And because of that system I described earlier, that terrain relative navigation, they believe they can get that kind of accuracy, right? So it's like throwing a baseball from London and hitting the tip of the torch on the Statue of Liberty in New York Harbor. That kind of ridiculous accuracy is what they're giving us. And I was delighted that, you know, after the launch and the cruise to Mars, they do these things called trajectory correction maneuvers, TCMs, and they had 6 of them planned. And the last ones, 4, 5, and 6, were supposed to happen over the last few days. And they just give you those slight little tweaking, get you on exactly the right place. They didn't have to do any of those. They canceled all of them because they are just right down the line on this trajectory. So that's really exciting. All right, I'm gonna hand over my microphone, unless you have another mic, Rick. Do you have another mic? Oh, okay.
Okay.
Why don't we let Mohini use that one? And why don't you guys come on in, you guys, come on in.
Yeah.
Sure. Hi, everybody.
Hello, hello, hello. So I can't quite tell from the masks. Can you maybe just introduce yourselves real quick? Actually, that would be awesome.
I'm Sammy Jacob. I'm a 4th-year PhD student under Dr. Jim Bell.
Great, Sammy, welcome.
Hi, I'm Ingenuity Helicopter. I'm a first-year PhD student with Dr. Jim Bell.
Hi, Mohini. Actually, I think your microphone may not be as working quite as well. Can you try again?
Hello.
Yo, perfect. Yes.
Awesome.
All right. So welcome, Sammy and Mohini. That's great to have you there. Can you tell us a little bit about what specifically, maybe each of you can go first, what it is that you're doing for the mission, what your involvement is right now, and also how do you feel this morning?
Yeah, so I can go. So for the Perseverance mission, I will be helping with operations of the MASCAM-Z instrument, as well as some documentarian roles that we have for all the planning meetings that we all attend in order to plan the science that Perseverance will be doing. In terms of my research at ASU, I actually work mostly with the Curiosity rover. So all of my research so far has been with the MASCAM instrument that's on Curiosity.
That's right. So I mean that's great to notice that ASU has has instruments on both of these rovers. So it has, of course, the camera systems on the current rover that's on Mars right now, the Mars Curiosity rover, and of course it'll have the MASCAM-Z system on the new one. So that, yeah. And maybe Mohini, would you like to go as well?
Yeah. So just like Sammy said, I'm also going to be doing some of the documentarian roles and things like that on Perseverance once it gets rolling. But aside from that, my research is primarily focused on mapping a specific part of Jezero crater to kind of add to our understanding of the landing site there. And then I'm hoping to use data that comes from the rover to actually, ground truth the research that I'll be doing.
Okay, no, that's great. So how do you feel this morning? I just wanted to ask about, what is the sort of, emotional state of where you are, and did you manage to get any sleep last night?
I mean, it's exhilarating to be here. I had just joined the Curiosity mission a few weeks before that one landed, but this is a much bigger ordeal today than the backyard barbecue we had to celebrate Curiosity's landing. So it's really exciting to be a part of this event today.
No, that's great, and I'm so glad you could join us as well. I know that there's actually, Mohini, I wanted to give you a chance to say as well. How do you feel?
Yeah, I'm super excited because this is my first time being involved in a mission, and yeah, I've always dreamed of having the chance to actually be involved in science like this. So it's been really awesome for the past year or so to actually be a fly on the wall in all of these sorts of discussions, and then to actually be at this point where it's about to land.
Oh, it's super exciting. So I have a couple of questions here from the audience. One's from Kathy Burnett, and she asks, what should a student study if they want to be part of the NASA team? So you guys are part of the NASA team, and so maybe you can say a little bit, both of you. Maybe Mohini, do you want to start?
Yeah, sure. So honestly, I think that there's a lot of things you can study in order to be involved with NASA, because there's obviously the engineering side that happens, and then personally, I'm coming at it from the geology standpoint. So I was focused more on earth science and things like that growing up, but there's also like geochemists and all of that. So chemistry and physics definitely also play a large role.
Mm-hmm. Okay, that's good to know. And maybe Sammy, did you want to add anything?
Yeah, I mean, I think Mohini covered it. I mean, we wouldn't be here today without an amazing group of engineers that built the rover and, built the models and the computers to land it today. But in terms of the science side, there's a lot of different topics that you can come at. So pick your favorite one and come join us at NASA.
No, absolutely. Actually, so there's somewhat of a related question, which I'm not sure if you would know necessarily, maybe, but this is from Shanuka Ramanujam, who asks, how can international students be involved in on these types of missions?
There are places for international students to get involved. I think probably the easiest is in terms of a PhD position, kind of like we are.
Right.
So
Exactly.
that would be my suggestion.
You
Or-
could mention the international teams involved too, right?
We do also have several international teams involved on the rover. So there are instruments built in France, Spain,
Norway.
Norway. So there's,
Yep.
not only can you come to the US and participate, but other countries are involved.
Yeah, no, that's great. So I mean, these efforts, of course, the whole Mars sample return campaign, which of course Perseverance is part of that entire campaign. That's a whole international endeavor. It's not just the United States. So I think that's great. Yeah, absolutely.
I'm lurking on the Q&A, Minnie. You could tell. I don't.
No, that's great.
I'm always lurking near my students.
He's always right there over the shoulder. That voice in the back of your head.
I guess a helicopter advisor, huh?
Hey.
No, actually, so speaking of helicopters, you want to tell us a little bit about the sort of fantastic helicopter that's on Perseverance?
Ingenuity.
Yes, I know.
It's going to be exciting to see how it goes. It'll be a couple of weeks before we set the helicopter down and see how it flies. But the Ingenuity Helicopter is a tech demo for this mission. So we won't use it for science as much as we will other instruments on the rover. But it's a good start to using these type of instruments for future missions.
Is it going to help in any way the Mastcam Z instrument at all in terms of scoping out kind of where, maybe you want to take images or any of that?
I think for this mission, maybe not as much, but that's kind of the general idea for future helicopters. It can do some aerial scouting for where we would like to drive the rover and take samples. This one, we just got to start and see if it flies.
Yeah.
That's true. That's a good answer. I would only add, Minnie, that it's really going to be the other way around. We're going to be helping the helicopter out because we can take movies, we can take video.
Okay.
And so when they do their flights, we're going to be pointing the cameras at the helicopter. The rover's going to be pretty far away, like 100 meters, a football field away, because they don't want the thing crashing into the rover, right? So they need high resolution cameras. We've got high resolution cameras. We can do videos. So we'll be taking those movies of the helicopter during its flights.
That's great, actually. So that kind of goes into the next question that Christina Day has. And she asks, what are all the different functions that Mastcam Z can perform? And so maybe whoever wants to take that.
You guys know the answer, right? That's all good. So, I mean, the still images, time-lapse images, movies. Can I show a model?
Yeah. Oh, yeah, absolutely.
So this is a model of the Mastcam Z. There's 2 of these up on the rover. Where am I looking here? 2 of these, one there for left-right stereo.
Oh, wow.
So that's about the size of a can of tennis balls for scale. And there's a zoom lens inside here that allows us to do that stereo from wide angle all the way to telephoto. So there's 3 little motors that drive a focus, the zoom, and then we have a filter wheel here. This round part is a 8-position filter wheel, so we can take pictures in red, green, blue, like our eyes see, or we can do a little bit of the ultraviolet and a little bit of the infrared, and so we'll make false color pictures that are sensitive to different kinds of iron-bearing rocks and minerals on the surface. But the real innovation, I wish I had 2 of these models, but there's 2 of them up on the mast, right? And that left-right pair lets us do stereo. So we're going to do a lot of stereo imaging with these cameras. So we'll see a lot of 3D with the red-blue glasses or special stereo viewers, Oculus headsets, and that kind of stuff. And then we'll be doing, flyover movie simulations of the landing site and all that kind of cool stuff. And I want to show off a couple more things. We have these little calibration targets that are on the rover deck. You guys see those? Can
No.
you see them there?
Oh, there we go. Yeah, now we can see them.
So these are little color standards. They have little colored circular chips and grayscales. And these are what we use, just like these photographers here will need to white balance. And we do the same thing with the sunlight on Mars, which changes all the time because of the dust in the atmosphere. So that's exciting. I have 2 more props. Can I show 2 more props?
Yes, please.
Okay.
We love props.
One is, I don't know if you guys can see this.
Oh.
There's a Hot Wheels model of the Mars Perseverance rover that's out now. So you can get it and play with it. And Karin told me I can't open the pack because that reduces its value. I'm going to do it. I'm going to open it up and play with it. Maybe not on the air, but so that's like one way that your project has hit the big time, right? But there's a more important way that we know. Where's my prop master, Alicia? Thank you. Here's how you really know you've hit the big time. Krispy Kreme donuts. A Mars Krispy Kreme donut. Special order today only.
Yes.
That means you've really hit the big time. So we're super excited about that too. Thank you. Okay, that's all the props I had.
Oh, that's great. Yeah, the donut's definitely my favorite prop. So here's another question here from Helen Coyle. And she asks, so this could actually go to each one of you that are on there. How do you feel to have contributed to this historic mission, to this historic landing? And how many members worked on the Mastcam Z team?
You can start, Mohini.
Well, I feel very excited to have contributed because when I started grad school, I didn't really think that I would really be able to launch into things. Pardon the pun.
Literally.
So so quickly. So it's just really incredible to have the chance to, you know, be a part of all of this and be a part of something that's so much bigger than myself, and, you know, hopefully for years to come.
No, that's good. That's great.
You're next.
Sammy.
Yeah, I mean, I'll echo Mohini's. It's an incredible opportunity to be a student, not only involved in the research and the science that Perseverance and other missions have done, but also be involved in the operations and to learn how the cameras work and how to, get the best data from them. I'm very thankful to those behind me who are processing the data. It's an incredible team to be a part of, and I think Jim would be the best for the exact number of how many of us there are.
Yeah.
Yeah.
Yeah, so Minnie, it takes something like 5,000 to 10,000 people around the world to do a mission like this. Total, when you count the people who built all the instruments, who did the designs, built the rover, built the components of the rover, built the subsystems and the subsystem components of the rover, built the rocket, launched the rocket, fly the rocket, and then do operations afterwards. Thousands and thousands of people. There's something like 400 to 500 scientists who are on the science team for the overall mission. And that is faculty members, staff, researchers, graduate students, undergraduate students, lots of different people from all around the world, universities, government centers, research institutes, literally around the world. So 500 or so scientists. And the MASCAMZ team is about 50 of those scientists from around the world, and more if you count the fact that many of them are faculty members who have their own student collaborators and some staff working. And that's around the country, and we also have Canadian members of our team, German members of our team, British members of our team, Austrian members of our team. So it's an international team for MASCAMZ. And of that 50 or so, it's about 20 plus or minus who are here at ASU, professional staff, faculty members, graduate students, undergraduate students. So we've got a great team of people. It takes every single one of us. None of these missions are done by any single individual or even small groups of individuals. It takes really a big team of people to do it. I have been just incredibly fortunate over the course of my career to have participated in every single one of NASA's rover missions.
Wow.
And so this will be my 5th time down these class 5 rapids that are going to come up shortly. And it is an adventure every time. There are butterflies and nervousness every time.
Surprised you don't have more gray hairs, Jim.
Gray hairs all the time. Yeah, I get some of that going on here. And every single one of these missions builds on the previous ones, and this one's no exception. This is the most ambitious Mars exploration mission ever attempted. And it's kind of cool to think about the fact that, since 1960, there's been 47 missions launched to Mars by the world's space agencies. And none of them have tried to bring anything back. But that's what we're trying to do. This is the first one. Parts of this rover, if we're successful, will come back. Small parts of this rover, about the size of a dry erase marker, with a piece of chalk size sample in each one of them, maybe 20, 30 of them coming back to the Earth from really well-selected places in Jezero Crater, where we've decided as a group of those hundreds of people where to drill, where to sample, what soil to scoop up, what atmospheric samples to grab. And those samples will be coming back. And amazing scientists like you, Minnie, will be working with them in laboratories like the ones that fill the basement of ISTB4 or other buildings here on campus and other campuses and institutes around the world. So that's what's different about this. That's why this isn't just, your father's or grandfather's Mars rover mission. This is new. It's exciting, it's cutting edge, and risky and fun.
Yeah, no, I think that's what's super exciting about it, is that this is actually the first step in sample return, the first time that we'll get samples back from another planet. I mean, we've got moon rocks, of course, our Earth's moon, but you know, anything sort of larger or planetary body, this is going to be the first time, and so exciting, because that's really, I mean, I think that's the key, just really finding out for sure whether there's life or not on that planet. I think is actually going to be that answer to that question is really going to be from the samples, I think. But anyways, super exciting. Actually, somewhat related to that is, you know, there's a question about, you know, I've heard two different dates for the pickup of the samples. It's 2026 or 2031. Which one is it? And so, did you want to try to answer that, or I could?
Yeah, it can't be 26. 26 is too soon.
Yeah.
Remember, we only get to launch every 2 years, every 26 months or so. So the next launch opportunity is in 22, late 22, early 23. And then it's going to, you know, take 6 months to a year to get there. So we wouldn't get there until 24 or so. But we haven't built the little rover that's going to go pick up these samples. We haven't built the lander that's going to carry that rover, as well as the rocket jetpack it has to carry to launch the samples into Mars orbit. They haven't built the orbiter that's going to be waiting for those samples around Mars. None of that is approved yet, although there's plans, there's ideas, NASA and the European Space Agency collaborating on that, on those ideas, but nothing is yet approved. So we got to do our job first, collect those samples. We expect it to take a few years at least, maybe more. But the latest I've heard is that, you know, the earliest launch would be in the late 20s, and therefore getting there in the early 30s, and therefore getting the samples back by as early as 2031 back to the Earth.
Exactly.
So about a decade from now.
Yeah, so keep our fingers crossed. It could be about 10 years or so before we have the samples back. So
yeah, I wonder, how are we doing on time? Because I'd love to show off some of the inside of mission operations. We've got a roving camera guy here who can follow us. That's something we can do?
Yeah, so it's about 12:23 here, and so yeah, we've got some time here if you wanna do that, Jim.
Are you set up to do that, Steve? I think we are. Okay, let's see if this works. This is an experiment.
Okay.
Take the handheld. Do you want me to turn off my remote? Okay. Testing. Can you still hear me?
Yeah.
Okay. Steve, you're coming this way? Okay, so Steve has his camera here, and oh, that's as far as you can come? Okay, why don't you come a little closer in here? And everybody say hi.
Hey.
Everybody say hi. This is our professional operations staff. So this is the Mission Operations Center. You see the big video screen with Mars up on the wall there. These folks are, let's see, Kristen, Kelsey, Laura, and Corinne are all going to be doing those operations tasks that we talked about, getting the pixels down from the camera, getting the telemetry down from the cameras, making sure that the cameras are healthy, they're working properly, they're taking the right pictures. We got all the pictures that we planned, and doing sort of this basic health assessment of what's coming back from the cameras. Oh, and there's Alyssa joining them there too. So these are our full-time staff. They'll be working around the clock eventually as we go into this crazy Mars time schedule, which we can talk more about. And this staff will also be being the first sort of vanguard of calibrating the images, creating the color pictures, true color, false color, as well as these beautiful mosaics and panoramas that we'll be cranking out to share with the public, to share with the rest of the science team. So this is really ground zero for Mastcam-Z here on the ground floor of ISTB-4. So that's a quick little tour mini of what's going on in here.
That's fantastic. It's great to be able to see that. Actually, we have a number of questions about Mastcam-Z that maybe, if you have time to sort of address some of those, that would be great. Well, what can you tell us about the resolution of the pictures that are going to be taken by the camera system?
Oh, I can answer. So we have the Z in Mastcam Z. See all these Z's all over our shirts and all that, right? The Z stands for zoom, which means we have variable resolution. We can go from wide angle to telephoto on the surface. And so at our best resolution, telephoto, looking down right at the ground in front of the rover, we'll be able to resolve, in other words, tell what they are, features that are about 1 millimeter in size. The pixel scale is a little smaller than that, but it takes multiple pixels to resolve a feature. So we'll see millimeter size features on the ground, little pebbles and rocks and veins and other things going on in rocks. That'll be kind of cool. Oh, my phone's ringing. And then off on the distance, when we still use our highest telephoto resolution and look off in the distance, we'll be able to see sort of centimeter scale, or maybe a little bit smaller. And the metric that I use is that if there were a good-sized housefly about 100 meters away, the opposite end of a football field, we would be able to tell that that's a housefly, not a little rock. So that's kind of the resolving power that we'll get. Now, that high resolution means a small field of view. So if we want to take big mosaics at high resolution, that's a lot of pictures that we got to snap all the way around, and that's a lot of data volume. So those will be rare. But our wide angle views will take a lot more big panoramas and landscape views with wide angle.
Okay, well, that's really neat. So here's another question here from Dennis Robertson. He says, to what extent do you build in redundant systems to account for equipment failures, unknown variables? Are there any redundant systems in Mastcam Z?
Yeah, that's a great question. And there are some systems on the rover. There are 2 computers, for example, totally independent. If something happens to the first computer, we switch to the second, and that runs the mission. There are multiple radio transmitters, for example. Something happens to one, you switch to the other. There are some systems on the rover that are not redundant. You know, there's only one arm. You know, there's only one sample handling system. Those would be too bulky, too expensive to duplicate. Mastcam Z, we sort of have redundancy in that we have 2 cameras. They're identical, except for just slight differences in the filters between them, but otherwise they're identical. So if we had a fault and a failure of one camera, we still have the other one. It would make it more challenging to do stereo, because we'd probably have to use one of the navigation cameras and one of our Mastcam Zs to do stereo. We could get by that way, but we wouldn't get the great telephoto stereo. So we would lose some capability, but still have a basic imaging capability to characterize the geology and help with operations for the engineers.
Hey, Jim, we have an astronaut on here who wants to ask you a question.
Astronaut? Who might that be?
Yeah, I wonder. Yeah, Scott Parazinski, who asks, what's the backstory with the cool Hawaiian shirts? Kawabanga Mastcam Z.
Absolutely, that's all Kristen. I don't know if you can see Kristen back there. Kristen, get Kristen. Kristen, stand up. Stand up.
No.
Stand up, Kristen. Kristen, can you see her? She's the Hawaiian shirts. That's all her. That's all her.
Okay, yeah. So actually, there's a related question. So what are some of the new technologies that you employed in the Mastcam Z sensors? And you know, what do they enable?
Yeah, so that's a great question. The sensor actually is the same sensor that we used in Curiosity. By modern standards, it's not super high resolution. It's a 2 megapixel array, which, you know, nowadays you go down to the electronics store and you buy 20 megapixel, 60 megapixel cameras, right? So why aren't we doing that? Well, again, those have not been proven in the space environment. Your iPhone or Android phone wouldn't survive the shocks and vibration of of launch, or the vacuum of space, or the crazy shocks and vibrations on landing on Mars, or the huge temperature swings day and night on Mars, that would break consumer electronics and especially sort of high-tech, super sensitive sensors. So the sensors that have been used before, in this case, perfectly fine and proven to work in the space environment. So we're using those. I think a lot of our advances in technology really are on the software side, on the image processing side, on the stereo processing side. We're bringing in a lot of the new visualization capabilities that are appearing, that have come out of previous NASA work, that have influenced the video gaming industry and some of those, image processing engines and things like that. Some of that's on board the rover in general, outside of Mastcam-Z, and some of it will trickle out into consumer electronics as part of the sort of normal trickle down from the space program. One of the ways we advertised Mastcam-Z in our proposal 7.5 years ago was that we don't need a lot of new technologies. We want to do this zooming. That's the big advancement. Some special lubricants and special machining, special tolerancing of very fine optical components. Some of those manufacturing techniques use high-tech machines that have come along in the last 5 to 10 years. But the system itself, NASA has a word for it. It's very high heritage. And NASA, we love NASA, but NASA is a very, very conservative space agency. They don't want to fly something in space unless it's flown in space already, which means you'd never fly anything new in space, right? So it's not quite that way, but the idea is we make incremental advances in our technology, or the manufacturing techniques that are used in our technology, or the materials that are used in our technology, and sort of improve things slowly, carefully, conservatively. And that's what our favorite space agency likes.
Yeah, no, absolutely. Here's a question from Matthew Cass, who asks, will the images taken by Mastcam-Z be available as STIL files so we can print out our own Martian rocks?
I have no idea what that file format is, but they will be available as PNGs and JPEGs, which almost all browsers will open up. So you should be able to convert them to your favorite format, print them on your favorite printer, wallpaper your house, whatever you want to do. We'll get you the high resolution images and panoramas on our public website, which is mastcamz.asu.edu. So the raw images will be going out on the JPL and NASA public website, probably starting sometime over the weekend if everything goes well soon. And then the processed images and mosaics that we make here at ASU will go out on the Mastcam-Z public website.
All right, great, thanks. Here's actually a question from Vivan Patak, who asks, when will Ingenuity take off from the rover? So this is about the helicopter now. So
yeah, Sammy knows the exact answer to that one.
All right.
Oh, sure I do. It's going to be a couple of weeks before we drop off the helicopter. So the helicopter sits attached to the bottom of the rover, and we kind of have to set it down and drive away. So it'll be a few weeks, but most of March is related to helicopter testing.
Okay, great. So here's a question from Tina Sindwani, who asks, this is insanely cool. I have a question about Skycrane. What will happen to it once it drops off Perseverance? Does it have any other functions planned?
No. You kind of, if you saw the video in the beginning, and maybe we'll run that again a little later,
Yeah.
or you could go to NASA and look at the video yourself. When the descent stage is called, with the retro rockets on it, it lowers the rover gently down to the surface and cuts those cables. It goes flying away and then blows up. We actually saw the plume from that explosion in the first Curiosity hazard camera images. My colleague Justin Mackey, helps run the engineering cameras on Perseverance, thinks that we might be able to see the plume again if it happens the same way. But it flies off. It's programmed to divert itself and get away from the rover and then crash somewhere a couple of kilometers away.
Wow. Yeah. So yeah, I don't think that's going to be doing much more after that.
Not much. No.
What a way to go, though.
Yeah.
So here's a question from Edgar Escalante, who asks, how many different institutions worked on this rover?
On the whole rover?
Yeah.
Gosh, institutions and companies,
Yeah.
it's hundreds from around the world. You know, on our cameras, so ASU leads the design and the science and downlink operations, but we worked with a small company called Malin Space Science Systems in San Diego. They have built a large number of deep space cameras, including our heritage cameras, the mast cam instruments on Curiosity. So they've got a great track record designing, building, testing cameras. We work closely with them in San Diego. That same group is doing our uplink commanding operations in San Diego because they have lots of experience and software already made for very similar systems for Curiosity rover. So we're tapping into that. But our optics was designed by another company called Synopsys. Our filter wheel and optomechanical systems were designed and built by another company called Motive. Our filters were built by another company called Materion. And each of those companies has their own vendors that are building, you know, providing the glass for the zoom lenses, or providing the transistors for some electronics, or providing the nuts and bolts. You know, you just keep going down the supply chain. Each of those vendors has their vendors. Each of those vendors has their vendors and suppliers. And I think the whole thing is actually built by teenagers in garages around the country at the end of the line. But hundreds and hundreds of companies, universities, research centers, and other organizations involved.
Yeah, no, I think that also answers Mindy Rich's question about how many kind of different universities are involved in this effort. So there's a lot, obviously.
A lot, yes. Yeah, we work with Cornell University, University of Hawaii, my alma mater, and Purdue, Western Washington University. What other universities am I forgetting? We also work with NASA Ames Research Center. We also work with Johns Hopkins Applied Physics Laboratory. I'm probably forgetting some more, but anyway, there's a lot of colleagues, and you know they're either working on hardware. The University of Copenhagen in Denmark, they're the ones who built our calibration targets in Denmark, so compliments of the taxpayers of Denmark for the most part. You know, other universities internationally, University of Winnipeg, University College London. So just lots and lots of collaboration.
Well, yeah. So I just wanted to say that Mohani's parents have a quick little note for Mohani, asking her, did you ever imagine this as a child doing this?
Well, it's funny that my parents are asking that, because they like to tell the story that I knew how to say all the planets by the time I was 2 years old in order. But and I had this like one book that was a space book, and I would just like flip through it a lot, and I used to love looking at that. So I've definitely been interested in space for a really long time. I don't think I could have conceived actually being at the forefront of the Perseverance rover as a child, though. So that's definitely very exciting for me now. Thank you for the question.
Hey, Minnie?
Yes.
I have an answer to the earlier question about computer speed. Our instrument manager, Greg Mihal, tells me, reminds me, I should remember this, it's a PowerPC 750 that operates at 200 megahertz.
Oh,
So
okay.
archaic by current gaming standards, but cutting edge for computers on Mars.
Yes, indeed. So, okay, well, here's another question from Alejandra Newell, who asks, how can the rover collect samples? What is the mechanism involved in collecting samples?
Yeah, that's a great question. And here's another example of an evolution in rover technology from earlier rovers. So Spirit and Opportunity had these little brushes, and they could scrape the surface off, brush and scrape the surface and grind a little bit, just a little bit into some rocks. Curiosity has an actual drill that can drill down, not too deep, about that deep, create a whole bunch of drill tailings and scoop the drill tailings up into the drill bit and into the rover's instruments inside the body, scooping that powder up that gets ground up by the drill.
Mhm.
So Perseverance takes the next step. The drill is not a regular drill, but it's a coring drill. So it has a hollow bit as it's drilling down into a rock. It encapsulates the rock and collects a core sample, like you'd see from the ice in Greenland, or sometimes geologists do this, or you see on a road cut, you see these long cores where they had to blast the road apart and sticking dynamite down there. We're not going to stick dynamite down the holes on Mars, but we're pulling out these core samples, like I said, about the size of a dry erase marker. It has that sample inside the bit. It then drops that bit into a carousel that you can see on the top deck of the rover. And that carousel then rotates that bit inside the rover. The bottom part of that carousel is inside the rover. And the front third of the rover is this whole system called the sample caching system. And that bit goes into a whole flow with a tiny little, there's a second arm on Perseverance that we won't see directly because it's inside the rover. It's like a tiny little Tyrannosaurus Rex arm that kind of moves around, grabs a sample, moves it from station to station, where it is hermetically sealed inside one of these empty capsules. We take pictures of it, make sure that there's actually something in it when it gets sealed up. And then the sample gets put back into a special little tray. And there's 43 of those sample tubes in that tray. And then we just have to decide when do we put them down onto the surface and how. And honestly, we do not have a specific plan. We could drop them one at a time like cookie crumbs as we go along, and some later rover can follow our trail and scoop them up. Or we could decide to geocache them or aerocache them in one spot and leave them somewhere out in the open or some obvious place for that follow-on mission to come get. Or we could do multiple caches in multiple places. This is all a strategy that we're going to have to figure out once we see what the place is really like, how easy or hard it is to sample, and also what the capabilities are of the sample return fetch rover that's coming after us, which we'll learn over the coming years as that gets developed.
Yeah.
So it's a great question. I wish I had an actual answer, but that's as close as I can come. Oh, I'll just mention one more thing. In addition to drilling, there's also a scoop. So instead of drilling, we can scoop up if we get to a sand dune or a really pile of dust or something like that, and we want a sample of that, we can scoop that into the sample tubes as well. So not just rocks, but we can get soils and dust as well.
No, that's great. Thanks, Jim. So, by the way, I have a question here from, actually more like a request from Angela Bell. Does that sound familiar, Jim?
Never heard of her.
No.
Hi, Mom.
She says your dad really likes the Hawaiian shirt, and can you please send him one?
Oh, sure. Fine. That's your question. Okay. Sure. All right, let's get Kristen on that order again. Reorder some more.
So here was Chris Genzel, who asks, I was curious if the two grad students speaking now could offer any words of wisdom to us undergrads who are looking to get involved in future research projects like this, maybe something that they've learned throughout their experiences that they wish they knew as an undergrad.
Well, I think the main thing that I've learned through my journey is that, like, don't be stuck on a specific vision of how you want things to go, because, like, there's so many opportunities that have come into my lap because I've been open to other things than, like, just going by the plan that I had in mind. Like, as an example, I thought that right after undergrad, I would want to go to grad school right away. But instead of that, I actually worked up in Flagstaff for a year before coming here. And I actually think that gave me a lot of connections to people and, like, made me into a stronger scientist before I started my PhD career. And if I had let, if I had just gotten stuck on the idea of going to grad school right away, I might not have had all of those opportunities, and I might not be sitting here right now.
Mm-hmm.
And also, I'll always just be grateful to all the people who help you along the way, because this is a really supportive community, and it's really nice to appreciate that.
Good words, Melanie. Thank you. Did Sammy want to add?
Yeah, I would just add on to Mohimi's is, just kind of jump in there and find a place to be involved. Ask your professors, other faculty in the departments if they have opportunities. I know that's why I am here today, is running into professors at my undergrad institute, which got me to my master's, which ultimately got me here. So just jump in and get involved, and sometimes they say no, and then you find a different opportunity.
Great. No, thank you, Sammy.
Graduated.
Here's a question from Judith Lyon, who asks, what's the most critical success factor? So I don't know whether Jim wants to comment on this, but
sorry, I missed the question. What was it?
So this is from Judy Lyon, who asked, what is the most critical success factor? What constitutes success for this mission?
Oh my gosh. So that really depends on who you ask. I can give you my answer. I mean, technically there's a list of sort of level 1 requirements: characterize the geology, understand details of the ancient habitability, prepare for future human exploration. And that's all great, and we have to do all those things. But to me, success is just having the different perspective that's going to come from this mission. And specifically, we've been looking at Mars from landers and rovers since the 70s through these robotic eyes, right? And that's what allows us to project ourselves there, the sense of vision, the sense of mobility with the wheels, the sense of touch with the arms, and smell with the chemical instruments, projecting ourselves and our hopes and dreams as field geologists out there through robotics, and experiencing Mars through robotics. And that's great, but for me, success on this mission is going to be seeing those samples with my own eyes. In your lab, Minnie, seeing those samples with my own eyes, and helping the world's geologists, geochemists, meteoriticists, and sample people really pull all of the subtle details of Mars out of these samples. Look at how much we leaped in our knowledge of the Earth and Moon with the Apollo samples, right? Yeah. It was an enormous leap. We wouldn't know a fraction of what we know about the Earth-Moon system if it wasn't for the Apollo samples. The same thing will happen with Mars. And that, to me, will be success.
Yeah, no, I endorse that viewpoint. I think that very much so. This mission is about the samples being brought back. Of course, I mean, and we have to understand the context in terms of the geology and the environmental history of the place, the astrobiological importance of the location. But yeah, ultimately that's to bring the samples back so we can actually do cruel and unusual things to them here in laboratories here.
No, it's all good. Rick tells me we have a special guest
Oh,
who has joined as a guest who needs to be graduated as a panelist to a panelist.
can we, Kim, are you able to do that? Or I don't see.
Yes, I can.
Want to be able to definitely include our guest here.
And how are we doing on time? We're doing okay?
Yeah, I think so.
Okay.
All right. Well, we're really pleased and honored to welcome President Crow. President Crow, welcome.
Thank you, Minnie. Nice to see you, Jim. Really exciting day here. Very, very excited. I guess I was just looking at the chart. We're still thousands of miles from the surface, but moving at a very fast rate of speed. So
definitely.
I guess it's the slowdown process that's the hard part.
It's the graceful slowdown process that's the hard part. Yes.
Yeah.
I just want to say congratulations to the whole team and the whole mast cam and the whole Z everything, and it's just really fantastic. And just want to say, this is going to be a fantastic day. Looking forward to not only the landing, but the chopper and the mast cam and everything that's going to be happening, and then the verification of water and microbes, which I know will be like instantly.
Pretty much, yeah. No promises on the microbes, but
no, we can't do that until we bring the samples back
exactly.
to the laboratories at ASU.
But I do assure you, we're going to one of the best places on the planet to look.
Yeah.
This ancient delta environment, these gentle sediments coming down from the ancient highlands, gently deposited like the end of the Mississippi River in a shallow body of water, beautiful layers exposed. We'll get pictures of them. They'll be beautiful, but maybe more importantly, those pictures will guide the detailed chemical and mineral instruments to go over there and study in detail, and then eventually drill and core and sample specific materials for Minnie's lab 10 years from now.
Yeah, I mean, that'll be fantastic. And then hopefully it won't be like some of the movies about coming back from Mars and stuff like that.
Yes, hopefully not. I agree.
If so, we'll work it out, right?
Your support, the administration's support at the university here, up and down the line. I mean, this facility that we're doing the operations, right? You and I talked about this a long time ago. This is why it's here.
Yeah.
It's here so we can do the operations on campus. We can involve the students directly. We can play a major role in NASA international projects and others right here from campus. So it's super, super exciting to see it come to life.
We're very excited, Jim. Very proud to be a part of all of it. And I'm just going to sit back and watch. So I appreciate you bringing me in for a second here. I'll just keep watching, and you guys can go on and do your thing here. So.
All right. Thanks, Mike.
Actually, so while we're on the kind of topic of ASU here, Jim, maybe you want to talk a little bit about the history of ASU's involvement in Mars missions?
Oh my gosh, ASU has been involved in much more than Mars missions going back to the history of the space age, back to the 60s. There's been someone here or groups here that have been involved, I believe, in pretty much every robotic mission of exploration that NASA has conducted to the moon and Mars and other planets. And of course, the Center for Meteorite Studies has been here since what, 1960, 1962, something like that, right? And been a major force in the world, the best university meteorite collection in the world. And those are, of course, samples of the moon, of Mars, of asteroids out there. And so, the legacy that was established by Carlton Moore, by Ron Greeley, the mantle that's been picked up by Phil Christensen and his group, so successful in so many different instruments and missions. And Phil and his team just got another instrument into Mars orbit last week on the UAE Hope orbiter. So very exciting about that. I was hoping that maybe somebody from that team would wander past and we get an update. But I think everything's going great in that mission. I'm not sure if they've turned the instrument on yet, but that's just, representative of what's going on here. Mark Robinson and his team still taking spectacular pictures of the moon at super high resolution every day with LRO. and Craig Hardgrove and his team building this tiny little shoebox size CubeSat that's going to orbit the moon when we get that ride from NASA's biggest rocket soon. And so it's, you know, there's just deep involvement in the entire history of planetary science and exploration. Astronomers working with Hubble Space Telescope, JWST, those are missions as well, and there's deep involvement here at ASU on those. Earth science missions, remote sensing, working with the big name Landsat and others, working with the new startups like Planet and others, and the things that we're doing in new space. I mean, it's just so many axes of things going on here that I can't imagine being in a more vibrant and exciting place.
Yeah, no, totally agree. So here's a question from Patrick Kelly. He says, actually, so he must be Dylan Kelly. He says, I'm Dylan, a middle school student, and I was wondering how much money it would take to make just one Mars rover.
Are you going to write a check, or are you going to do like PayPal or Venmo? What's your, okay. No, it's a great question. There's a lot of data on this. You can go to the Planetary Society's website. Casey Dreyer, one of my colleagues there, has done a detailed analysis of the cost of NASA missions. And so Perseverance is actually less expensive than Curiosity was, because it's made from something like 90% spare parts from Curiosity. You know, these are generally one-off kind of special boutique vehicles, if you will, boutique spacecraft. But NASA doesn't just build one set of wheels or one main computer or one mast for the cameras. There's always a spare, flight spare. Just in case something happens to the main one, they can swap the spare in. And so once Curiosity was off, launched, and successfully on Mars, those flight spares just sitting around, and there were plenty of spares available to build almost all of a new rover for hundreds of millions of dollars less than what it costs to build Curiosity. Now that said, they're still expensive. These are multi-billion-dollar, $2.5 billion missions to build these vehicles. And of course, that money isn't blasted off into space. That money is all spent here. It's mostly people. It takes, you know, that 5,000 to 10,000 people that I talked about earlier to build these things over many years, 3 or 4 years to build them and test them and launch them and get them there. So that money is spent over multiple years, and that's about it's a fraction of the larger NASA budget. The whole NASA budget is about a little less than 0.5%, 0.5% of the federal budget. And the planetary science is about 1/3 of that, maybe 1/4 of that. And the Mars program is about 1/3, maybe 1/4 of that. And so, you know, in absolute dollars compared to what the government spends overall, it's not a lot of money, but it is still a lot of money to do these big kinds of missions.
Yeah, great. Thanks, Jim. So here's a question from Tyler Connolly, who asks, how was and why was the landing site for Perseverance chosen?
Yeah,
You
so
wanna jump in? Go for it.
landing site selection process took years after the mission was selected. We had public input at the beginning to kind of find really cool areas on Mars, and then scientists started investigating them, and it was quickly narrowed down to just a few that we ultimately got high resolution images of from orbit to understand the science. And Jezero was picked mostly because of this large delta that's near our landing site. So that's a feature we've never really gotten a rover to on Mars. So it's a new feature for us to explore. And
so that's like a river delta here on the Earth, right? I mean, it's kind of almost very similar to that from the pictures, at least, right?
Right. Yes. Very, you know, It's thought to be a very similar formation environment long time ago on Mars that formed this delta, and others that Mohini will be looking at for her PhD.
Yeah.
Right. Great. Yeah. So the other question now here is from Anna McNally, who asks, how will samples that the rover collects get back to Earth? What is the actual, we sort of implied how it was going to happen, but maybe Jim, you want to talk a little bit more detail about how that's going to happen?
Sure. I mean, I can tell you what the plan sort of is today, but it's going to change. But the basic outline is during our mission on Perseverance, we'll collect the samples and we'll drop them onto the surface individually or in small collections called caches. And they're in these metallic tubes. They're hermetically sealed. The tubes are painted so that they're not going to get too hot or too cold. Being metallic, they'll be easy to find, and we're going to put them, we're not going to hide them or bury them. We're going to put them out in the open and then move on and continue to do other things with the rover. But we'll know right where we left them. And a new mission that NASA and the Europeans are working on designing right now together will send a lander, a small rover called a fetch rover, and a launch vehicle called a Mars Ascent Vehicle, or MAV, M-A-V. That lander will carry those two components and land near where we left at least one of those caches of samples. And the rover will drive off the lander, follow the footprints, the wheel tracks of Perseverance, find that cache, have an arm capable of picking up those samples, putting them into a sample canister, probably spherical, somewhere between the size of a grapefruit and a soccer ball, okay? And stuff something like maybe up to 30 of those tubes into that sample canister. Bring the canister back to the lander. There's this little rocket sitting on the lander, puts the canister in the rocket, backs off to a safe distance. Somebody at NASA pushes a button, says launch the rocket. The rocket launches up into Mars orbit. Waiting for that, then, that sample canister inside the rocket is another orbiter that NASA and the Europeans, perhaps others, are working on designing. That's primary job is to get to Mars, go into orbit, and find the sample canister. Okay, that kind of rendezvous, robotic rendezvous in orbit. The sample canister will be metallic and shiny and hopefully easy enough to find. We'll know what orbit it's in from the rocket that put it there. Capture that sample canister into the orbiter, rocket out of Mars orbit, rocket back to the Earth, like the OSIRIS-REx mission is doing with its samples, like the Japanese Hayabusa and Hayabusa 2 missions have done with their sample canisters. Get back to the Earth, release the sample canister, which then parachutes down to the Utah desert to a gentle, soft landing where technicians and others go capture it and lovingly bring those samples into the laboratory. What could possibly go wrong?
Yeah, such a,
That easy.
oh my God, such a complicated dance.
Very complicated. But none of it, well, all of it rocket science. I was going to say none of it rocket science. No, it's all rocket, but none of it like crazy Star Trek warp speed, none of that. It can be done. It's got to be carefully engineered. We got to figure out how to pay for it. We got to figure out how to work the international collaborations so we can get multiple contributions. So there's a lot of engineering that has to be done on it, but I believe it's achievable within a decade or so.
And I think, I think important to remember that the components of all of those things we've done before, but it's just sort of putting it all together. It's gonna be fun. So here's a question from Nitin Mishra, who asks, if we find positive signs of life on Mars, how does it help us now?
Yeah, no, that's the question that's kind of driving the mission? What can we learn about the origin and evolution of life on our own planet? What can we learn about the presence, existence, and form of life elsewhere in our solar system, in our galaxy, and beyond? You know, if indeed there was another planet in our own solar system where the conditions for life as we know it were there early in that planet's history, where it was habitable, which previous orbiter, lander, rover missions tell us there were such places on Mars. If we find that and find evidence that life did in fact form there, maybe it's long gone, maybe it's now underground, whatever, but if we find evidence that, you know, life did form there and thrive maybe at least early when the planet was more Earth-like, that is spectacular. That tells us that life is probably everywhere in our universe, right? That anywhere you find habitable conditions, maybe statistically, it's inevitable that life appears and develops. So that could be, you know, profound in terms of our search for the big questions that we go after, right? Are we alone? How did we get here? Right? These are questions that now, with our technology, with the space program, with the advances in our understanding of life on our own planet, you know, we're in a position to try to answer those questions. And the focus on Mars, those 47 missions since 1960, is because it's the closest place to home where we can test that hypothesis. Are we alone? And so that's why so many of the world's space agencies, so many planetary scientists and others are so excited about this. It's why astrobiologists are excited about Mars. Sure, they're excited about Europa and Titan and Enceladus and other places in the solar system where there could have been habitable environments, could still be habitable environments, and we're doing missions to those places, and we should, but none of them are as easy, in quotes, because what we're about to see is not easy. None of them are as easy to get to as Mars. And so that's why we've been focusing on the red planet to try to answer some of those big questions.
Yeah, no, great answer, Jim. So you mentioned the HOPE mission just now, and the fact that our own Phil Christensen has an instrument on it. There's a question here from Edward Zinker who asks, is the US team coordinating in any way with the UAE and the Chinese teams on their missions?
So I don't know if anybody from Phil's team is on the line who could answer, but I mean, I know that the ASU team, the team in Colorado that helped to build the spacecraft, they're in close coordination all the time with their colleagues at UAE, working very closely with their scientists, with their engineers, with their mission planners, with their government space agency. So yes, lots of coordination there. I'm not aware of specific collaboration that we have with the Chinese. And so there's just a lot less known about that mission. I know, you know, they did get successfully into orbit, which is great. They have plans to land a lander and a rover sometime this spring. And my assumption is we'll find out more as the Chinese Space Agency decides what to do. They'll release that information and let us know. But we're all obviously rooting for them to have a great, successful mission too.
Yeah, no, it's really fantastic that there's three missions that are currently just, you know, getting to Mars, and sort of underlines the fact that you talked about, you know, the launch windows that are available to get to Mars. I mean, there's certain, you know, there's a cadence that sort of leads to some of these things stacking up like that. But it's so exciting to have, you know, so exciting to have three missions there. And hopefully there will be coordination if there's not already. So, so JD asks, he says, you know, following up on Jim's point about the rover, the Mastcam-Z actually looking at the helicopter or the drone, can Mastcam-Z actually track Ingenuity?
Yeah, that's a great question. We've been, you know, we've been trying to figure that out. We don't know. We know we can at least set a wide field of view and watch it, you know, kind of go up and down in the field of view. Part of the problem is we don't know the details of the helicopter's flight plan yet. But you know, I'm inspired by the fact that the NASA animation artists, when they show the animation of the mission and the helicopter, you're watching the end of the mast and the cameras are going like this. And they're following the helicopter. It's like, yeah, can we do that? It's in the movie. Can we do that? You know, so we don't know. It's probably too complex for this particular mast azimuth altitude system. But if we can, we will. And it also depends upon the flight path and the flight speed.
Here's a question from Jessica Machino, who says, you know, what is the first image that Mastcan Z will take?
Okay, there's two answers. One is kind of a sad and boring answer. The sad and boring answer is that tomorrow, so the mast will still be stowed on the deck of the rover and the cameras are staring down into the deck. And it's pretty dark, but we'll take a couple of pictures just to make sure that the cameras are operating. And we'll get those pictures back, and they'll be the most boring pictures ever sent back from Mars because they'll be kind of all black. But they'll be noisy, and there might be a little bit of light leaking around the edge of where the cameras are nestled against the deck. And so while we won't probably see anything interesting, we'll at least know, hey, our cameras are alive. Those are going to be our first two pictures that we get back. We've taken similar pictures on the cruise to Mars. And they're similarly, it's dark inside there. There's no lights or anything. There's no window to look out. So those are also dark, but they tell us cameras are working. And if there were light, we'd get great pictures. So what we have to do is we have to wait until Saturday. On Saturday, they'll pop the mast up, and then we can open our eyes and see Mars, and we'll take a picture of Mars scene. We'll take pictures of our calibration targets on the deck. We'll test out the zoom. We'll test out the focus. We'll test the filter wheels. And hopefully we'll get a bunch of pictures back Saturday night or Sunday and then into next week, depending upon their priority and how long it takes them to come down.
Okay.
So the second answer is more fun than the first one. But the first one's important.
Yeah. So the next question is from Jack Coulter, who asks, has anyone considered using a solar-powered light aircraft, such as a balloon or a Zeppelin type equipment with cameras to use on Mars, or is the atmosphere too thin for such a craft?
Well, you know, the helicopter is solar powered. It does have a solar panel that recharges its battery. So there's an example of a solar powered, pretty light aircraft. But if you're talking about a balloon, I don't know of any specific plans. I've seen, you know, fanciful ideas and concepts that you could certainly, you know, a helium balloon will float in the Mars atmosphere just like it floats in the Earth's atmosphere, because the gas is CO2 dominantly. So hydrogen or helium or some lighter than that air gas will work the same way. So it could be done. I haven't seen, you guys know of any specific plans? I haven't seen any specific plans, but
No.
it's something that could be pursued for the future.
So Donna Bader asks, are those face masks with the Mars 2020 logo available to the public?
That's a good question. Where'd they come from?
These red ones that Jim and I have are available. It was an online shop. I think it was Star Loris. Corinne is one of our swag masters, and she's the one who found them all. But they are online if you go Google it.
Search for those, yeah, okay. Here's another question from Beverly Youngstrom, who says, how did the Jezero area get its name? What is the significance of the name?
Yeah, so a lot of craters on Mars, especially sort of medium to small craters, are named after cities and towns on the Earth. The International Astronomical Union does the official naming, and there are lists of cities and towns that have been proposed. And Jezero, which I think is pronounced Jezero, is, I want to say, Bosnia-Herzegovina maybe, or Serbia. It's a town in that part of the world that the crater is named after. So, and it was named long before it was chosen to be a landing site for the rover.
Okay. So here's a question from Craig Bell. Any relation to you, Jim?
Never heard of him.
He says, I have trouble keeping my glasses from fogging up while wearing a mask. How does Mastcam Z keep the lenses clear and protected from the Martian elements?
Yeah, that's a great question. Excellent question. So, Craig, I'll show you my model here, my prop, okay? So this outer part here is a sunshade. And if I turn it at a little angle, you might, yeah, you see some of the veins in there, right? So that keeps scattered sunlight from bouncing around inside the lenses. But otherwise, it's just the front lens is open to the environment. And so we don't have any wipers. Nobody's going to be up there, you know, no service call, not yet. So when we're not using the cameras, we point them down on the mast, and that prevents dust from settling out of the atmosphere on them. But when we are using them, of course, we're pointed out at the landscape, and the wind is coming along and it's blowing dust in here. And one of the things we discovered on Curiosity is that not just dust, but sand bounces up somehow a couple of meters, 6 feet up high, and gets dumped inside these little front lenses. And so it's not on this model, but on the real Mastcam Zs, we drilled 3 holes here, and it's little drain holes. So the idea is if we get sand in there, and we've seen that happen on Curiosity, we'll basically just kind of go zzz, 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 and drain the sand out, give them a little side-to-side shake, up and down, and we'll get the sand coming out of there. But the front lenses will get dusty. That's happened on all previous Mars cameras. You know, I wear glasses a lot. Anybody who wears glasses, you know, you take your glasses off and look at them, and they're probably really filthy. They're covered with all kinds of hairs and crap and stuff. But you can see through them just fine because that stuff is really so far out of focus. And so in general, the dust on the lenses isn't really going to bother us. We don't, from past rover experience, we haven't done any special wipers or anything like that. And then the other thing that happens is, you know, you're just kind of taking pictures, and a dust devil or a small windstorm will come along and blow the dust off the lenses and clean them. We've seen that happen multiple times on previous missions too. So Mars is our cleaning service. That's our plan.
Yeah. Here's a question from Mark Weiser, who asks, since we talked about Mars donuts, are there any Easter egg surprises on Perseverance like Curiosity's wheels?
No comment.
Well, actually, can you talk a little bit about the Curiosity's wheels Easter egg there?
Yeah. So I mean, I can say that there are you know, logos and some little messages and tributes on the rover that you'll see over the course of the mission. Many people probably saw the NASA press release about the medical symbol, you know, the staff and the serpent for the medical world, paying tribute to all of the emergency responders and caretakers and others who've been helping us get through COVID. You know, the teams, especially the launch team, had to work through COVID to get the rover to the launch pad on time because the planets line up and you got to go. You can't wait. And so that tribute is on a plaque on the rover. We've got a tribute to some previous rovers, a little marching army of rover icons from the previous rovers that have been to Mars. That's a little bit of a tribute. There's a NASA plate that has one of these microchips with signatures of everybody who signed up to get your signature on Mars, get your name on Mars. That's on the rover. On our calibration target, we have some fun little education and outreach elements, a little story about life on Earth and its connections to Mars, a little motto, a secret motto around this, secret message around the side of the rover that's too small for the cameras to see. So we know that it's going to get read by astronauts and settlers on Mars someday. And we wrote a story about that on the MassCamZ public website on our blog there at masscamz.asu.edu. You can check it out. Some of the other instruments have little logos and little messages and stuff like that. So yeah, there's a whole bunch of fun little embellishments. NASA calls it festooning. That's what it's officially called. Spacecraft is festooned with some embellishments, and they have to be approved by NASA and all that kind of stuff. And but yeah, there's some memorials and tributes and some art really on the rover as well that we brought along with us. So that's kind of exciting and fun.
Oh, that's great. So here's a question from Bruce Feldhusen, who asked, have you found precursors to life on Mars?
Ooh, that's a good question. You should answer that question, Minnie.
Yeah, that's an interesting question. I mean, I think, you know, I know that there's been detections of things like methane on Mars. I know that Curiosity actually saw some blips. I mean, things where the methane actually sort of seemed to increase and then decrease. And so it's been suggested that maybe that's indicative of some kind of life existing there. I don't know about precursors necessarily, except that, you know, thinking about prebiotic types of components like carbon and nitrogen. I think we know that those materials are there. But yeah, I think, you know, we're some of these precursors, so-called precursors, are not necessarily indicative of the fact that life will definitely be there. But right. Yeah.
And the methane story is very controversial. We don't really know what's going on there. And, you know, and in a sense, you know, asteroids and comets are raining down precursors to life on all the planets all the time. You know, these organic molecules that have been found in meteorites like the ones in CC's collection here and others. So the starting material is out there in abundance. And it's all about how those materials can get more complex in the presence of liquid water, heat sources, or other energy sources to, you know, become biologic.
So here's a question from Seth Levine, who asks, the Curiosity rover is still operational on the surface of Mars, and how far apart are these two rovers going to be, Perseverance and Curiosity? And will they ever come within visual range of each other?
You know the answer?
I don't know the exact distance.
It's easy to remember.
Oh, yeah?
1,000 miles.
Hey, there you go. Oh.
About 1,000 miles apart, and no, they're never going to get within visual range of each other, unfortunately.
And here's one from David Cam, who asks, are there any artificial intelligence algorithms used for MassCamZ in the actual camera and the downlink control and operations?
Not directly in our operations, but there are a number of people in the machine learning and AI community who work with data like we will collect to do image processing later, to search for interesting color signatures or textural signatures. I work with a group at JPL that does that. One of my former graduate students, Hannah Kerner, did her thesis work on those kinds of algorithms. So not directly in operations, but certainly in data processing and image processing and analysis afterwards.
Okay, yeah. So here's somebody who's asking about a mission to Jupiter's moon Europa. Actually, just wondering, is there going to be a mission there soon?
Yeah, you know the answer to that one, don't you?
I do. Yes. Yes, there will. It's one called Europa Clipper that's in works, and there's a number of ASU faculty involved in that too. And let's see. So I'm actually I'm wondering about the time. Actually, we're getting close to.
Yes, we are. So it should be. You should see the cruise stage solar panels separate from the rest of the descent stage in about 13, 14 minutes. So I wonder if, I don't know what's going on NASA TV, but do we want to switch to that feed, or what do you guys think? Or take some more questions, or is this NASA TV? Oh.
So By the way, I do have Greg Mihal's answer here. He commented, he's part of the HOPE mission. He's an ASU member of the team for the HOPE mission. And he says that ASU is working directly with UAE team on flight operations, and we have not collaborated with the Chinese yet. So, you know, that's still an open possibility here, but
Great.
so let's see if, do we want to take some more questions? What do you think, Jim?
I'm just wondering what's going on the live NASA feed and whether it's interesting enough yet that we should switch over to it.
While they're trying to figure, while they're trying to figure that out, maybe I can ask you one or two other questions.
Sure.
Okay. So here's a sort of a general question. George Emmett asks, what's the oxygen level in the Mars atmosphere?
Oh, extremely low. Very, very little free oxygen, and no ozone layer to speak of tiny, tiny amounts. And most of it, you know, the atmosphere is like 95% CO2. Most of the rest is like argon, and tiny amounts of oxygen, water vapor, and other trace gases. And most of that oxygen coming from the solar ultraviolet light breaking down CO2, splitting the CO2 molecule and freeing oxygen in that process. So a lot of it in the upper atmosphere, very high up, but very little free oxygen close to the surface. So nothing like the 20% that we have here on Earth.
Yeah. So yeah, we're definitely going to have to carry it over the astronauts going there. We're definitely going to be able to only breathe if they have external tanks or something.
Yeah, and they should bring a sweater too.
Yeah.
Thinking that's going to be a good idea. Yeah.
Indeed. And sort of a related question from Christopher Senti. He asked, do you think it would be a good idea to terraform Mars?
Well, you know, that's a great question. And, you know, we sort of get at the boundary between science and science fiction here. You know, to change the climate of a planet takes centuries. You know, we've been working on it for a better part of a century and a half on our own, and we're starting to do that on our own, certainly in small ways, but important ways. But to change a planet that is so dramatically different than the Earth, Mars, to change its climate and atmosphere into an Earth-like environment is not something that we're technologically capable of right now. And even if we were, at the rates that we could do it, it would be millennia, thousands and thousands of years to do that kind of thing. You know, should we do it ethically? It would be, I guess, useful to know if there is an indigenous population there, maybe microbial, and then we'll have to ask ethical questions about, you know, what we do about that. But people are going to, the reality is people will settle Mars and other places in the solar system in the decades and centuries ahead. And so I'm kind of punting the question, but these are important questions we're going to have to ask ourselves. How do we deal with those environments, and how do we learn to truly sustainably live off the land in such hostile places? And of course, what can we do to improve life back here on the Earth by learning how to be sustainable in incredibly hostile environments? How can we make it better here? How can we be more sustainable here? That's an important product of the space program, that knowledge.
Indeed, yeah. So actually, Kelly Reading asked a question that's probably on a lot of people's minds at this stage. When will EDL begin? Entry, descent, and landing. When's that going to start?
Yes, so in 9 minutes, we should see the separation of that solar panel cruise stage from the rest of the descent stage and the heat shield and all that. That's supposed to happen at 1:38 Arizona time. And then the spacecraft will cruise in that configuration for about 10 minutes. And about 10 minutes later, it hits the top of the atmosphere and the heat shield will start to heat up and friction and all that. And that's the beginning of the so-called 7 minutes of terror that'll get us to 1:55 Arizona time landing. And we should be hearing and seeing the mission operations folks at JPL give sort of a live feedback as they're getting different signals from the spacecraft all on the way. So we're going to want to switch over there and watch that pretty soon.
Yeah, what are you seeing over there, Jem, in terms of whether we're going to be switching over here pretty
Looks
soon?
like we're seeing a feed from JPL, so we might want to switch over that. And
So let's go ahead and switch over just for a little bit, see how things are going. We can kind of do a little assessment of how they're doing, and we'll
Yeah,
go from there. So
I'd
Seth,
be happy
go
to
share your screen.
stop talking and just do a lot of listening from now on.
Yeah, it's starting to get exciting.
Thanks, Minnie.
Sure, thanks, Jem.
All right. Now, Rob, you've been right where the Perseverance team is sitting now. What's in store for them as we approach landing?
Well, this is this is the nail biting time. Fortunately, we still have ones and zeros coming, but very soon, as we approach cruise stage separation, the transmitter on this rover we've been using all the way to get to Mars is going to be turned off. So we will lose our ability to see ones and zeros. But the good thing is, once the cruise stage is gone, there's another radio that will continue transmitting a tone, so that like a flashlight, that will allow us to at least see that the vehicle is still on, and that color of that flashlight tells us a little bit what state the rover's in. But soon after that, it won't be very long before we'll be able to hear more ones and zeros coming from the spacecraft. So this is a really exciting time, and it's just important to remind people this is there's a lot that can go wrong in a day like today. There are thousands of things that have to go right.
Yeah, we had success in the past landing on Mars. You'd think it gets easier, but it really doesn't. Why is it still so difficult?
Well, it's because it's involved thousands and thousands of things, hundreds of thousands of lines of code. There's 79 pyrotechnic devices. Each have to work perfectly. One critical wire short, or one key thing mechanism that doesn't work or breaks, and it's mission over. And so it's, and it's very easy. We're human beings. We're not perfect. Mistakes can be made. We count on each other to find our own mistakes, and we work very hard to learn from the mistakes of the past. We've had many failures. Remind people, roughly half, around half of the missions to Mars over history have failed. And so it's that could happen today too. Even though we've had a nice, wonderful string of successes in the United States, it's still still a bit of a gamble that we have hoped that we have erred in the side of luck, and we've stacked the deck and loaded the dice to make this thing succeed. But if we do fail and something bad happens today, I can tell you, we're going to learn it. We'll have the data that tell us what happened. We'll know why. We'll figure it out. And if we are allowed, we will pick ourselves up and get us back on the horse. And if Congress and NASA allow, we will try again. As we always do, we will learn from our mistakes.
And what are the possible scenarios we could be looking at today?
Well, there's things like one of the key stressful elements for all of us is parachute inflation. But just even separating from the cruise stage is a pretty major event. Lots of devices have to work properly. Certainly, the heat shield separation, getting the descent engine started. There's no less than 16 rocket motors that have to work. 8 to control during entry, another 8 to control it during landing. I said, it's a lot of stuff, and it all has to work. And guess what? We haven't done this before with this vehicle ever. This is this first attempt to actually land. We can't try this on Earth. We can't we don't have test pilots to try it out on this planet before the big show. So this vehicle is doing it for the first time. We've done the best testing we can do in bits and pieces, but it's as best as we could do. But I think our team is up to it. This team is the best. It's a diverse, intelligent, amazing group of people. People from all over the world who worked on this, not just here in California, but all over NASA, contributors from aerospace, universities, countries around the world. It is just an incredible, remarkable engineering achievement. And I am just so proud of this team.
Thanks, Rob. Now let's listen back into mission control.
Right, we're about 14 minutes from entry interface. The vehicle is currently preparing the heat rejection system that has kept the thermal system cool inside the air shell for about the last 6 months. This will allow the spacecraft to more easily cut the line in upcoming cruise stage separation, which is under 4 minutes now.
We have now enabled the rover pyro bus.
That's the pyrotechnic system that's
We are
going to
powering off the cruise stage devices.
and these are the things in the cruise stage that we no longer need. With the pyrotechnic system working, we can explode the devices.
The vehicle is preparing for the upcoming cruise stage separation in about 3 minutes 15 seconds by powering off all the devices on the cruise stage in order that they can be safe once the cruise stage is jettisoned.
Yeah, this cruise stage has been very reliable.
We are firing our first pyros to vent the HRS liquid and gas.
This has been the coolant that's kept our vehicle from getting too hot on the way to Mars. We have to vent it into space. And this is one of the first major events that take place as part of entry, descent, landing.
The HRS vent anchor is complete.
Yes.
We will see the next anchor in approximately 3 minutes.
Okay.
We are currently 12.5 minutes from entry interface. We are coming upon cruise stage separation in 2 minutes and 20 seconds.
What's happening now, Rob?
Okay, well, we're just waiting. The rover is completely in charge. It's doing all the things we've taught it how to do. It's all built into the software. We've tested it over and over and over again. This team has spent 24 hours a day, 7 days a week testing this thing for years. And so this is really the culmination of all that work. So this vehicle is getting ready to push that cruise stage away. Once it gets pushed away, the entry system with the rover inside, with the rover still in charge, is going to get ready to take the vehicle, turn it to the right orientation, and aim it to Mars, and prepare for entering the atmosphere. This won't be long. Be prepared for this event.
We're about 1.5 minutes from cruise stage separation, about 11 minutes, 20 seconds from entry interface.
Okay, so it's about 10 minutes from cruise stage separation till entering the top of the atmosphere. From then on and out, things happen
We are switching
fast.
to MFSK tones. Telemetry will have stopped.
Telecom is confirming that the spacecraft has switched to broadcasting tones. These tones are received directly from Perseverance, but have very limited information content. We won't receive real-time information until about 9-10 minutes from now, once the Mars Reconnaissance Orbiter starts relaying information from Perseverance. We are under 1 minute from cruise stage separations, about 10.5 minutes from entry interface.
It's getting exciting. I have to admit, I am quite anxious, but very hopeful that this machine is going to do what we asked it to do.
You're seeing the heartbeat tones.
Okay, that means that there's no more ones and zeros coming. It's just the vehicle telling us it's still alive.
We're continuing to receive tones from Perseverance, standing by for cruise stage separation. We have indication that cruise stage separation has been confirmed by the spacecraft.
We're off on a good start.
In about 1 minute, Perseverance's landing software will wake up and begin the final preparations for entry. The first action it will do is to fire warm-up pulses with its entry thrusters. These pulses ensure that the spacecraft gets the thrust that it wants during entry interface. We're about 9 minutes from entry interface.
Okay, so now the vehicle's on its own. It's turning itself into the direction of facing the heat shield toward Mars, and will eventually hitting the top of the atmosphere. We're not far away. This is going to go very quickly from here on out.
That's confirmation that we got shadowed by the cruise stage as it passed through our beam to the Earth.
Telecom indicated actually that we could see a signal that the cruise stage went between the Perseverance entry capsule and Earth. So we saw a little blip, the data stream indicating the cruise stage separation. We have confirmation that the vehicle has started warming up those entry thrusters. Warm-up pulses have begun. At this point, the spacecraft is trying to stop its spin from the cruise 2 revolutions per minute down to 0, and then will turn to its desired orientation from entry. It will separate the 2 balance masses that has kept it balanced during all of cruise. This will allow the entry capsule to have lift when it enters the atmosphere. We have confirmation that the spacecraft has turned to the desired entry altitude. We are about 7.5 minutes from entry interface.
Okay, the vehicle is pointed in the right direction. The thrusters are warmed up and doing their job. And now we've spun down from 2 revolutions per minute that the vehicle had the whole way to Mars. It's a spin stabilized spacecraft. And then from here on out, it's going to just be a bullet, and it's going to control its orientation and attitude via rockets on the back of that back shell.
Points carrier lock. Sorry, the DTE from the radio science from Green Bank reports carrier lock. You see the carrier on the downlink.
Flight level 1.
We are continuing to wait for entry interface. We're about 6 minutes and 45 seconds from entry interface. We have confirmation from Greenback that they are receiving direct to Earth telemetry via that path. The spacecraft Perseverance is currently transmitting heartbeat tones. These tones indicate that Perseverance is operating normally and has nothing significant to report. This is as expected. We're currently just over 6 minutes from entry interface.
Okay, now we wait. As soon as we get to the top of the atmosphere, it'll be very quickly, which is the entry point. It won't be very long before the atmosphere will start getting thicker and thicker. It's going very quickly at a fairly steep angle of 15 degrees into the atmosphere. And as it starts to slow down.
Just under, we're about 5.5 minutes from entry interface. We're still receiving heartbeat tones. We expect to continue receiving heartbeat tones until about 5 minutes after entry. At that time, Perseverance will be no longer in view of our antennas here on Earth. About 90 seconds prior to entry, the Mars Reconnaissance Orbiter should begin receiving telemetry from Perseverance and streaming it to Earth in near real time. There are a few expected short outages, such as when we have a plasma blackout or when we enter the peak heating phase. Aside from these outages caused by the plasma blackout, antenna switching, or high dynamic events, spacecraft events, we should have telemetry until about 90 seconds after landing. A plasma blackout is when the signal from Perseverance isn't strong enough to make it through the superheated, super fast air flowing around the spacecraft all the way down to Earth. Once the temperature drops below that peak heating, we do reacquire the signal from Perseverance. We are currently about 4.5 minutes from entry interface. Perseverance continues to report heartbeat tones, indicating everything is nominal.
Okay, what we're looking for now is Mars Reconnaissance Orbiter should be in view soon of our vehicle and be able to listen to ones and zeros coming from a separate radio that's really designed to talk between spacecraft.
MRO reports the electro radio is powered on, ready to receive signals from the lander.
Okay, MRO is ready and able and waiting for the to hear from our rover.
Mars Reconnaissance Orbiter has reported that it's ready to receive the signals from Perseverance. It should be in a few minutes here. We're just
Flight local 1
from entry interface.
We don't need these 1s and 0s, as Swati said, but to land safely, but we really need it for our own health and well-being today, to keep our nerves under control. But
around this time, a second spacecraft, Maven, should begin picking up telemetry from Perseverance and will continue to record that telemetry until several minutes post-landing. We won't get that data for several hours after landing as it's being recorded and then will be forwarded to Earth later. We are continuing to receive heartbeat tones, indicating that everything is nominal. We're currently at about 3 minutes until entry interface.
okay. Very soon we'll be getting 1s and 0s, I hope, from our radio on the rover. The entry interface is nothing more than just an arbitrary place in the sky that we've defined to be above the atmosphere. But from that point on, there's definitely atmosphere, and above it there isn't.
We are 2 minutes from entry interface. Perseverance is to transmit heartbeat tones, indicating everything is nominal.
So the tones can tell us whether something's bad or not is happening. So far the heartbeat is doing well. So the vehicle thinks it's in good shape to land, which is a great sign.
Sure.
We're just under 2
Reading this
minutes from entry
John Wesley
interface.
Powell.
As it gets closer to Mars,
He says, we
Perseverance
have
is
an
actually being
unknown
pulled
distance
in
yet
by
to
gravity
run,
and
an
accelerating.
unknown
By
river
the
yet
time
to
Perseverance
explore.
reaches entry interface
What
point,
falls there are, we
it
know
should
not.
be going just
What rocks
under
beset the
5.4
channel, we
kilometers
know
per
not.
second.
With
We're at
some
about
eagerness and some
90
anxiety
seconds
and some
from entry
misgivings,
interface
we enter
and
the canyon
standing by
below
for Mars Reconnaissance
and are
Orbiter
carried
to pick up
along by the swift
the
water.
telemetry.
Goosebumps? Goosebumps, everybody? Yes. We're about to be carried along by the swift water, right? Pretty exciting.
We are 1 minute from entry interface.
MROs are in receive mode.
We have confirmation that the Mars Reconnaissance Orbiter is now relaying data from Perseverance. We're about 30 seconds from entry interface. Perseverance is going about 5.2 kilometers per second and is about 190 kilometers altitude above the surface of Mars.
Confirm your jet data flow.
About seconds from entry interface. 5.3 kilometers per second and an altitude of about 150 kilometers from the surface of Mars. Perseverance is currently going 5.3 kilometers per second at an altitude of about 120 kilometers from the surface of Mars. They have confirmation of entry interface. Perseverance is currently going 5.3 kilometers per second at an altitude of about 120 kilometers from the surface of Mars. The ship is now waiting until it begins feeling the atmosphere of Mars to slow it down. Once there is enough atmosphere, it will start controlling its path to the landing target. Navigation is also confirming that we can see a little bit of that slowdown of the atmosphere on the Perseverance entry capsule. Our current velocity is about 5.36 kilometers per second and an altitude of about 67 kilometers from the surface.
We are probably seeing MRO plasma blackout at this point.
The vehicle should be doing its turns right now.
MRO has lost lock.
Perseverance. We have indications that Perseverance is now performing bank reversals in the atmosphere. These are the steps in order to control its distance to the landing target. Perseverance has just passed through the point of maximum deceleration and has indicated that it felt approximately 10 Earth Gs of deceleration.
MRO has lock again.
Yes, 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 yes.
We saw a small outage of the UHF telemetry from Mars Reconnaissance Orbiter during that peak heating phase, likely caused by the plasma blackout. Perseverance is still continuing to perform bank reversals in the atmosphere to control its distance to the landing target. Perseverance is going about 1 kilometers per second at an altitude of about 16 kilometers from the surface of Mars. We have entered heading alignment, which means Perseverance is no longer trying to control the distance to Mars, but to the target on Mars, but instead is flying straight to the target.
Parachute.
Our current velocity is about 550 meters per second at an altitude of about 15 kilometers from the surface.
MRO is reporting good telemetry lock.
We are coming upon the straighten up. We are starting the straighten up and fly right maneuver, where the spacecraft will jettison the entry balance masses in preparation for parachute deploy and to roll over to give the radar a better look at the ground.
Yes, yes.
The navigation has confirmed that the parachute has deployed and we are seeing significant deceleration in the velocity. Our current velocity is 440 meters per second at an altitude of about 12 kilometers from the surface of Mars. Perseverance is now slowed to subsonic speeds and the heat shield has been separated. This allows both the radar and the cameras to get their first look at the surface. Current velocity is 145 meters per second at an altitude of about 9.5 kilometers above the surface.
Yes, yes, yes.
Perseverance now has radar lock on the ground. Current velocity is about 100 meters per second, 6.6 kilometers above the surface. Perseverance is continuing to descend on the parachute. We are coming up on the initialization of terrain relative navigation and subsequently the priming of the landing engines. Our current velocity is about 90 meters per second at an altitude of 4.2 kilometers. We have confirmation that the lander vision system has produced a valid solution and part of terrain relative navigation. We have timing of the landing engines. Current velocity is 83 meters per second at about 2.6 kilometers from the surface of Mars. We have confirmation that the back shell has separated. We are currently performing the divert maneuver. Current velocity is about 75 meters per second at an altitude of about 1 kilometer off the surface of Mars.
Here in Safety Bravo.
We have completed our terrain relative navigation. Current speed is about 30 meters per second, altitude of about 300 meters off the surface of Mars. We have started our constant velocity accordion, which means we are conducting the sky crane, about to conduct the sky crane maneuver.
We've lost direct to Earth tones.
As expected. As expected.
Sky crane maneuver has started. About 20 meters off the surface.
We're getting signals from MRO.
UHF is good.
Touchdown confirmed. Perseverance safely on the surface of Mars. Taking the stand of class life. At this point, the descent stage has flown away to a safe distance. Perseverance is continuing to transmit direct through Mars Reconnaissance Orbiter to Earth.
Oh my God. Oh. Oh.
MRO reports they're still getting telemetry from the lander.
All right, all stations.
We got it. We're
Touchdown
there.
confirmed. We're going to wait for the images.
Wow.
This is so exciting. The team is beside themselves. It's so surreal. Stay tuned. We might get some pictures. So much.
It is as expected.
MRO is still seeing a strong signal from the lander.
You just heard the news that Perseverance is alive on the surface.
We've just heard the news that Perseverance is alive on the surface of Mars. Congratulations to the mission. And looks like we have some more news in. It looks like we're getting the first image. Here, take a look at the first image.
Right, this is OL3. I have the target point on the map when you are ready. We are ready, OL3. Go for it.
We're looking at some rocks on Mars. Pretty exciting. That's
I'll
the
be
first
moving
picture
in,
coming down from
showing
the
you
wide-angle
the safe
fisheye
zone that
lens
we've landed in.
on the front of the rover. And looks like a nice, pretty flat plane to land on. That's good news. Didn't land on a big boulder or anything bad.
Has just put the first image from Perseverance on the surface of Mars. Now it comes from the engineering cameras known as the hazard camera. This camera is mainly used to help the rover drive safely around Mars, and we will get higher resolution photos later in the day.
A little later tonight, there'll be a big burst. Start to include the descent movements. So we get movie cameras all over this thing. As the parachute came out, there was a camera watching the parachute. Nice. Sky crane. There was a camera watching the rover go down on the sky crane and a microphone. So we'll get movies and sound over the next few days from everything that just happened. Pretty spectacular.
Second image in. Our second image is in.
Okay, these we have a camera in the front and rear of the spacecraft. They're near the ground, so these are pretty close. You can see the wheels there, and they're a little dirty because we've got glass covers over these cameras. But we took these seconds after landing, so there's still dust in the air from our landing event. So this is happening. This happened just seconds ago. Just arrived, and this is really amazing. And we even know where we landed. This is the most amazing thing. The vehicle has told us where it's landed because it figured it out. This is a sign. NASA works. NASA works. And when we put our arms together and our hands together and our brains together, we can succeed. This is what NASA does. This is what we can do as a country. On all of the problems we have, we need to work together to do these kinds of things and make success happen.
Joining us now is the acting administrator of NASA, Steve Jurasik. Steve, welcome and congratulations.
Hey, thank you. What an amazing day.
And how does it feel to have another rover on Mars?
It's amazing to have Perseverance join Curiosity on Mars, and what just a credit to the team. I mean, just what an amazing team to work through all the adversity that goes and all the challenges that go with landing a rover on Mars, plus the challenges of COVID, and just an amazing accomplishment.
And what does this mean for NASA and its future plans?
So for robotic exploration, every time we execute a mission with new instruments, we discover new things and things we never thought we would discover. So that always informs our future robotic missions, both landers, rovers, and orbiters. This mission also has technology on it. One of the cool things is the Ingenuity Helicopter. It's an experiment on this mission, but if it's successful, we can use it as an science observation platform by putting instruments on it, and also use it as a scout for future rover missions. And then just the entry, descent, and landing capability. It'll allow us to land more larger, more ambitious robots on the surface of Mars. And then for human exploration, we have the Mars Entry, Descent, and Landing Instrumentation, which is going to give us EDL information. We have the Mars Environmental Dynamics Analyzer. It's going to give us size and properties of dust particles, because when we send people, we're going to have to deal with that dust. This is just an incredible mission because of the science and the technology, and then caching samples for our Mars Sample Return mission. That will be an amazing mission, the first round trip to Mars and back. and bringing those samples cached by Perseverance back to Earth to examine with state-of-the-art equipment in our laboratories here on Earth.
We have so much to look forward to. And we also have a student question coming in from Landon. Let's take a look.
Hi, my name is Landon Applegate. I'm in 6th grade and I'm going to Academy for Academic Excellence. And my question is, do you think we could get resources from Mars to help on future missions or even as like a launching point?
Great question, Landon. Actually, we have an experiment called the Mars Oxygen In Situ Resource Utilization Experiment, or MOXIE, and it's going to demonstrate generating oxygen from atmospheric CO2, and that could help generate breathable oxygen, and even if we can liquefy it, oxidizer for propulsion systems. So that's a tech demo on Perseverance. And then we're going to continue to characterize the frozen water on and below the surface of Mars, and eventually try to figure out how to extract that water from the Martian soil, or what we call regolith. And then we can use that for potable water and also break it down into oxygen and hydrogen for rocket fuel. So absolutely, we're going to try to eventually figure out how to live off the land to support human missions to Mars.
Thanks for taking the time to talk to us today,
Jim.
Steve.
Thank you.
We-
And now,
How do you feel? Oh my God.
safely touched down on Mars.
I'm going to Disneyland. Woo! It feels like we just won the Super Bowl and the World Series and Pro Bowlers Tour, you name it, whatever. It's like just awesome. And the team here is totally on top of the downlink, and to get those first pictures, those wide angle from the fisheye cameras in the front and the rear, and to see we've got a safe place to drive. We're not like in some giant boulder field. We're not on the edge of some cliff.
We can actually see some rocks.
See some rocks,
awesome.
right? We love rocks,
Yeah,
right?
we do.
Yeah. So that's cool. And these are low resolution. We'll get some more telemetry in a couple of hours from one of the other orbiters. And then tonight, overnight, there'll be just a really big downlink pass. It'll get the high resolution versions of these with the covers off. Remember, these have the dust covers on.
Right.
And it's still kind of dusty there. You can see from the retro rockets, right?
Yeah.
And so tonight we'll get the high res versions of these, and then we'll start downlinking the movies of all of this. All of this was recorded by video cameras and microphones on the rover as it was coming down.
No more simulations.
It'll be the real deal, right?
Real
When
deal.
that parachute deployed, we'll see the movie of parachute going out.
Wow.
The rover dropped down the bridle. We'll see the sky crane maneuver from above, and we'll see the landing site images that it took and processed on board.
Wow.
And then tomorrow we'll get our first boring Mastcam Z images as the mast is all tucked in.
Yeah. Oh,
And then
there
on Saturday, when the mast pops up, we'll get our first real images of Mars. So
How
that's
exciting.
super
How exciting.
Yep.
How does the team feel all around us? I guess we see all of some of our Mastcam Z team members here. How do you feel? Oh no, it's
just another day in the office at CC, right?
Just exactly.
Just another day in the office.
Yeah, exactly.
Super exciting.
Yeah, then this is just the beginning. I mean, it's going to be super exciting for the next couple of years. It'll be.
So we are officially all going to be working on Mars time now. The Mars day is 40 minutes longer than an Earth day. So we got the downlink at 1 o'clock today. Tomorrow it'll be 1:40. Then the next day it's going to be 2:20. Then the next day it's 3 o'clock. And so our work day is going to be shifting through the Earth work schedule as well. Oh, they picked out that they've got the landing site image.
Oh,
that's where we landed, right there. Woo! Right next to the front of the Delta. Excellent.
Wow.
Excellent.
So we know exactly where we
We
landed.
know exactly where we are now. Yep. Because the rover told us that because it used its pictures it was taking as we were descending to line up with a map that we gave it on board. It lined it all up and it knows right where we are.
Wow.
Yeah.
So was that within that kind of landing ellipse that we had identified?
Actually,
It's already right in the center. Oh, look at that. Wow. So amazing. So amazing.
Kind of where we wanted to be. We didn't want to land on the Delta.
No, right.
We want to be able to drive up to it and see those beautiful layers as we approach.
Wow. So, hey, what are you going to be doing to celebrate?
Probably analyzing telemetry. I don't know. We'll have to figure that out later. We're just looking forward to getting to work. Really,
Yeah.
we've been waiting for this for a long time.
Any other parting words from you, Jim, before we close things down?
No, just
this
super excited
webinar?
to be able to share this with so many of our friends and family and special friends at CC.
Absolutely.
And great questions that came from everybody.
I know, incredible. And
know?
I'm so sorry that we couldn't get to so many of the
Yeah,
questions because we
yeah.
we were inundated with questions.
Yeah, yeah.
And I just hope, we answered a lot of
Yeah,
questions,
yeah,
but we had a lot.
Yeah,
So-
no, and it was a great technical support. Rick, Meg, Kim,
Yes.
Karen, the whole team.
Our
Everybody,
amazing
great
team.
job. All
Yeah.
the docents, you guys, just beautiful work getting this out there and
Yes.
sharing this with everybody. So thank you.
Yeah, thank you so much
everybody.
to our community outreach group, which has been just incredible, the kind of support that we have. So I just want to say a few final words. Just want to thank everyone for being here, joining us for this very exciting webinar. And, we're so happy that it was a success. The landing was a success. And so now it's going to be, from here on out, some exciting data. So thanks very much for joining again and hope to see you at another opportunity.
Thanks, everyone. Oh.